So Stephen, we do record our seminars and post it online. Is that okay with you?
Yep, that's fine.
All right, thank you. So welcome everyone. I'm going to introduce my speaker today. Today we have Professor Stephen Lowe from California Institute of Technology. He'll be talking to us about learning and control in power distribution grids. Dr. Stephen Lowe is a Gillian Professor of the Department of Computing and Sciences and the Department of Electrical Engineering at Caltech. He's an awardee of IEEE Infocom Achievement Award and the ACM Sigmetrics Test of Time Award, and is a fellow of IEEE, ACM, and CSEE. He received his BS from Cornell and PhD from Berkeley, both in electrical engineering. Thank you so much, Professor Stephen Lowe, for you to being with us, and back to you with your presentation.
Thank you very much, Anamika, for the kind introduction and also the invitation. So let me share my screen. Okay, great. Okay, I'll talk about learning and controlling distribution networks. And I guess we all are familiar why we are interested in this. In the US, 84% of total greenhouse gases are due to energy use. And of this 84%, electricity generation and transportation, they consume about 2/3 of all energies in, say, 2019. So primary energies are coal, gas, petrol, hydro, nuclear, and renewables. And they emit between 55 and 60% of all greenhouse gases in the US. And therefore, if we want to drastically reduce greenhouse gases, we have to electrify transportation and we have to generate clean energy source, clean energy. So that's what we have been interested in. And distribution network in this context is becoming increasingly important because a lot of the active distributed energy resources will first appear in distribution systems. So they, on the one hand, introduces fluctuations in supply, in demand, in power qualities, and therefore increases the risk of blackouts. But they are also intelligent and network distributed energy resources that many are capable of real-time computing, communication, and control. And therefore, you can figure out how to do this, then we can improve robustness, security, and efficiency. So let me tell you 3 pieces of work in this context. The first is learning the network admittance matrix. Very often when we think about control and optimization, we assume we know the network. And in distribution system, for example, very often we don't. So how do we use measurement to try to figure out the admittance matrix in distribution systems? The second piece of work, so the first piece of work is in collaboration with Yue Yang, who was a postdoc at Caltech, is now a professor at Huazhong UST, Omid Alakanian at University of Alberta now, and also Claire Thomas at Berkeley. And the second piece of work is mainly done by a former postdoc at Caltech and now a faculty at CMU on learning-based voltage control. So the idea is that suppose we don't know the network, can we go directly from feedback data or the measurement to control? And in this context, controlling the voltages on the distribution system. And the third is about electrification of transportation. So I want to describe a live testbed for EV charging that can be useful for smart grid. It's open source, so hopefully it'll be useful for people here. Okay, so the first topic, learning admittance matrix. So I formulate the problem, and then I'll just tell you the final result on exact identification for radial networks. So the problems is as follows. We have a network which we can think of as a graph, G, with the set of nodes or buses, N, and also the set of lines or links, E. And each line, JK, is parameterized by a single complex number, which is the series admittance of the line. So if you think about the pi model, then we are assuming that the charging admittances at each end of the line to be 0. So each line is characterized by one parameter, which is the series admittance, YJK. Sometimes I use YJKS, superscript S. So that's the simple model. And the Kirchhoff law basically give us the current injection in each node J can be related to the voltages on the network. And in vector form, we have this I equals YV, where I is the vector of all current injections. So these are current phasors at each node in the network. V is the voltage phasor vector in the network, and they are related linearly by this admittance matrix Y. Because we assume the admittance, shunt admittances are 0, and therefore the admittance matrix Y has 0 sums. Right? So this will be the JKth entry corresponding to a line JK, and this is a diagonal entry, which is the sum of the rows, right? So with a sign difference. So for us, a admittance matrix is simply any complex symmetric matrix. So it's not Hermitian, it's complex symmetric, and that's why a lot of the complications in computation arises, the fact that it is complex symmetric. So the issue is, when we don't know Y, can we identify Y from measurements? So more precisely, suppose we have measurements of the current phasor injection at node I at each time t, and also the voltage phasor Vi at each time t. And therefore, at each time t, we have this I equals YV equation. So I, again, is the vector of all current phasors, and Vt is the vector of all voltage phasors at time t, and they are related through this admittance matrix Y. Now, if you look at the ith row at time 1, then this is ith row at time 1 of the equation, the vector equation above. So II at time 1 equals the ith row of the admittance matrix Y multiplied by the voltage vector for time 1. Right? So you fix at node I and just look across time and stack them up, you get this. So this is the situation at node I, but at time t equals 2, right? So equals voltage measurements at time 2 multiplied by the ith row of the Y admittance matrix. So you set them up across all the time, you get this equation. So I superscript t is I of t is the current at node I, but across time. And this is the voltages at all nodes and all times. So that gives you the matrix, and then you form a row vector, the ith row of Y, right? So you get this. And therefore, if we assume we have exact measurement of all the currents at each time and all the voltages at each time, and if we assume the voltage measurement vector, this vector V, is full rank, then we can identify the admittance matrix Y exactly. More generally, if we have measurement noises, for example, then we can formulate a regression. So we've given the voltage measurement, so this is a matrix, given the current measurement, which is another matrix, we want to choose a admittance matrix, so any complex symmetric matrix, so as to minimize the L2 norm, Frobenius norm squared. Subject to the constraint that the admittance matrix is symmetric and 0 row sums. Okay, so you can formulate this problem, and given the measurements V matrix and I matrix, you can get an estimate. If Vt, as I said earlier, has full column rank, and if there's no error, so you get exact measurements of V and I, then you can identify the ground truth Y exactly. Otherwise, if you do have error, then this solution of this regression will give you a minimum cost estimate of your Y admittance matrix. Right. So there are many ways to do this, and people have studied this problem and you propose different methods to do this. We want to look at a different problem. So this formulation assumes you have measurements of voltage and currents at every node in the network I. What if you don't, right? So the problem that we focus on is the following. So the setup is that we have a radial network connected, and let's assume for now it is single phase. It can be generalized to 3-phase, but I will stick to single phase in this talk. And suppose we have measurements of voltage phasor, current phasor at a set of nodes I that are what we call measure nodes. So this is the set of nodes where we do have measurements of the voltage and current phasors. h times t. And then the remaining nodes are what we call hidden nodes, where we don't have measurement. And a key assumption is that at every hidden node I where we don't have measurement, we assume there's no current injection. So this is reasonable that if you do have an injection, then typically you have a generation or you have a load at that bus I, and typically you want to meter them, at least let's say to charge them for payments. And therefore, a key assumption is that we don't measure every node, but for those nodes where we don't have measurement, we assume there's no current injection. Okay. And then there's a technical assumption, which is not that important, that every hidden node has degree at least 3. So that's the setup. And the problem, so in that case, let's group I1, which is a subvector of all the voltage current phases, into 2 groups. So the first group, I1, represents all the measure nodes. So these are the measurements of the current, and the remaining nodes are hidden nodes, which we assume has 0 injection. Similarly, we can group the voltages into 2 groups, V1 at the measure nodes and V2 at the hidden nodes. And accordingly, we can decompose the admittance matrix into these 4 blocks. So again, the issue is we have some measurements on the current, and then some measurements on the voltages, partial measurements, and can we figure out the admittance matrix Y? So here's the situation, and this is one example where there's a hidden node. So the yellow or orange is a hidden node, and the green nodes are the measure nodes. And this is the equation that relates the voltages and the currents. So we can look at the Cron-reduced admittance matrix given by this, which is Schur's complement. And this admittance matrix Y bar for the Cron-reduced network relates the voltages and currents at all the measure nodes. So I1, which is the set of nodes where we do measure, and V1, which are the voltages at those measure nodes, is related through this Y bar, that is the Cron-reduced admittance matrix. So pictorially, this describes the Cron-reduced graph, and its topology and line parameters is given by Y bar. Okay, so that's the definition of Cron-reduced admittance matrix. And you can show that the Cron-reduced admittance matrix indeed is admittance matrix in the sense that it is complex symmetric. So if you have measurements only at the set of measure nodes I1 and V1, so this will be the matrices, then you can use the same formulation as before and try to figure out what is Cron-reduced admittance matrix Y bar, right? Subject to the constraint that Y bar is symmetric and has 0 row sum. So you can apply all the techniques that people have developed for this problem and try to figure out what is a good Y bar, right? So for one thing, is because Y is complex symmetry, even if you look at the submatrix or submatrix, which will give you the Schur's complement Cron reduction, there's no guarantee a priori that it is invertible. So unlike if it is a real symmetric matrix, then it is guaranteed that it will be invertible. But because of the complex symmetry, you need certain conditions. So you can show, fortunately, that if the lines are resistive inductive, which seems reasonable, then indeed the Cron-reduced Y admittance matrix exists, and therefore you can apply the methods for the full measurement case. And similarly, if or the voltage measurement matrix has full rank, and if there's no measurement error, then you can identify this exactly. Otherwise, you can identify with a certain error. So the question that we ask is, suppose we can identify exactly the Cron-reduced admittance matrix Y bar from the measurements, which is given by this, in terms of the blocks of your original admittance matrix Y. The question is that can you identify the ground truth, the original matrix Y, from Y bar, right? So, and therefore, if you are given this graph with the line parameters, can you do the inverse problem and figure out what is the admittance matrix for the original network? Surprisingly, the answer is yes. So you can exactly recover both the topology and impedances for the radial network if you have an exact chrome-reduced admittance matrix. And the proof is by construction. So it gives you basically a iterative algorithm. It's a finite algorithm that will recover the original ground truth Y from Y bar. So let me just, okay, so pictorially to visualize, suppose we have a network which is a radial network, single phase. The green nodes are the measured nodes. The orange nodes are the hidden nodes. So suppose we have measurements at the green nodes, the voltages and currents, and at the orange nodes, there's no current injection. Then it turns out if we can recover exactly the chrome-reduced admittance matrix, then we can figure out the original matrix for the entire network without knowing anything about the hidden nodes. So we don't know the topology, we don't know the number of hidden nodes, we don't know the line parameters on those hidden nodes. It turns out you can still do that. So let me just give you a rough idea of 3 key observations underlying the proof. One is that it turns out you can decompose. So we assume that our starting point is Y bar, right? So suppose someone give us a chrome-reduced admittance matrix and ask, can we figure out the original matrix? So we start with that. It turns out you can decompose the Y bar, the chrome-reduced matrix, into sum of 2 matrices, basically. And that decomposition allows us to identify internal nodes and boundary nodes. A internal measure node means that it's a node that's surrounded by other measure nodes. So it doesn't have any neighbor that is hidden. A boundary measure node is a node, is a measure node, but it has both neighbors that are measured and hidden, right? And similarly, a internal or boundary hidden nodes are those nodes that are surrounded by only hidden nodes or have also measured node as its neighbors. Right? So once we can identify this, we can arrange the original admittance matrix in a certain form that will allow us to recurse. And the recursion is what gives us a finite algorithm to compute the original matrix Y. So let me go into a little bit detail. So again, you have the starting point is the chrome-reduced admittance matrix. We want to decompose them into Y1 bar, Y2 bar in terms of the blocks or submatrices of the original matrix Y. Now, of course, we don't know these submatrices of the original Y, and therefore we don't know Y1 bar nor Y2 bar. But we know that we can decompose in this particular manner. Well, it turns out that if you look at the graph corresponding to Y bar, right? So this is an example. We have a chrome-reduced graph that we can write down given Y bar. It turns out if you look at the graph, you can decompose the graph into 2 graphs. So the graph of the chrome-reduced network is a sum of 2 G1 bar and G2 bar, where G1 bar is a disjoint collection of trees. It's a forest. So this is G1. And G2 is a disjoint collection of clicks, maximal clicks. So these are the clicks. So this is G2. Once you decompose the graph in this manner, then you can actually figure out Y1 bar and Y2 bar. So just to recap, details are not too important, just the high level idea. From the measurement of partial measurement of voltage and current phases, suppose we can figure out a chrome-reduced admittance matrix. Do the all sorts of different algorithms that we can apply for regression. From that, we can decompose the graph into G1 and G2. One is, again, is a forest, one is maximal clicks. From that, we can figure out the line parameters for Y1 bar and Y2 bar. But these are not the original Y admittance matrix, but they consist of the computed from submatrices of the original matrix Y. But from Y1, Y2 bar, it allows us to identify which measure nodes are the boundary nodes, which are the nodes that have both neighbors that are measured and neighbors that are hidden. Right. So this is one example. And similarly, we can identify the boundary hidden nodes. Right. that allows us to arrange the original matrix Y into a certain form. Again, we don't know what the individual blocks are, right? So we only know the Schur's complement of this matrix, but we know it has this structure. Once you can identify this with a set of boundary measure nodes, this is a set of boundary internal measure nodes, then we know Y can be arranged into the structure, even though we don't know the individual submatrices, those blocks. Okay. But once we put the Y into this structure, that allow us to. So these are the internal links. Right? So these are the measure nodes and the connectivity among them. This is the boundary links that connect a measure node to a hidden node. And these corresponds to the hidden nodes, which we know nothing about. We don't know the topology, connectivity, nothing. But we know Y has this structure, even though we don't know those individual submatrices. But this structure allows us to compute Y in a recursion. So instead of describing algebraically what that recursion is, let me just show you pictorially what that recursion does. Okay. So this is an example where we have a network. So the green nodes are the measure nodes and the orange nodes are the hidden nodes. A solid green node are the internal measure nodes. So this is internal measure nodes, and a empty green nodes are the boundary measure nodes. Similarly on the hidden nodes, so the empty orange nodes are the boundary nodes. So the boundary nodes are the important ones that we focus on. Once we have the Cron-reduced admittance matrix through the graph decompositions and stuff, you can figure out the line parameters of between two measure nodes. So all those green lines, so they are known. Okay? These gray lines are unknown. So we don't know the line parameters, and we may not even know the connectivity. So that's a starting point. Okay. So now what the recursion does is that it will allow us to compute the line parameters of these lines between a boundary measure and a boundary hidden nodes. And therefore, after one iteration, these line parameters are known. And therefore, the original boundary measure nodes becomes an internal node, as if they are internal nodes now. And the original boundary hidden nodes now becomes a boundary measure node. And therefore, we are exactly in the same situation, but with the ring surrounding the set of hidden nodes shrunk by one layer, basically. And then you can repeat. And then you do the same recursion, you shrink further, and eventually you cover the entire network. So that's how you can figure out the entire Y admittance matrix. Okay, so let me go on to the second one. So the first one, again, is from partial measurement, can we figure out the network? The second piece of work is done by Guanan Qu, who is now a faculty at CMU. And the question is, suppose we want to do Vauban control, but we don't know the network. Can we still try to basically implicitly track? We'll see some parameters of the network and go directly from the data to control, right? Without explicitly estimating the network parameters. Okay, so the problem is well known that we have more and more DERs on the network, and sometimes the voltage may get out of bound, and we want to control the reactive power in the network to bring the voltage back within safety limits. So there's a lot of progress in the past decade on these problems. So there are standards and then different formulations, different control algorithms, a lot of them. A limitation of this set of work, including our own in this area, typically assumes that we know the network, we know the topology, we know the line parameters. We also often, ourselves, our own work included, use linearized model. So the disfold model is the model by Baran and Wu back in 1989 at Berkeley. So we used a linearized version of the disfold model for radio networks. So The issue is that often we don't know the topology, we don't know the line parameters, and then of course, the power flows follow described more accurately by nonlinear models. And therefore, can we still do worldwide control without model information and also taking into account of nonlinearity? And he proposed a way to do that, which uses online learning from the data to deal with the lack of model, and then adaptive Jacobian tracking. I'll go into a bit more detail what that is, to deal with the nonlinearity. Okay, so the problem formulation is that we have a network, distribution network, whose voltage, so V is the voltage magnitude square, is a vector, so it's the voltage magnitude square of all the voltages at all nodes in the network. It is a function of the reactive power at the nodes. So Qt is a vector. If there's a reactive power, controllable reactive power source, then there's a Q at that node that will be controllable. Otherwise, it is a constant or is zero if it's not controllable. So the assumption or the formulation is that suppose you measure the voltages on the network, and then based on the voltage measurement, you make a decision to adjust your controllable reactive power, apply to the network, and then you close the loop. So given Q of t, you get a certain voltage vector V, which you measure, and which then you feed into the controller, you choose the next Qt, right? So that's the control. And suppose we do this control iteratively, and then eventually we want to converge to a steady state where the steady state will solve this problem. So we want to minimize a certain control cost. You can think of this as a control cost, subject to the requirement that in steady state, after this feedback control converges, that the voltage on the network as a function of Q satisfy the voltage limits. Okay, so that's the model, very simple. And the challenge is that the voltage depends on Q nonlinearly, and therefore this is a non-complex problem. More importantly, we don't even know V, right? We don't even know the network. Right? Okay, so how do we deal with this problem? If the traditional method, if we assume the network is linear, and if we know the network, then the voltage depends on Q in this Fi manner. So X is a matrix that depends on reactances on the network. P is the real power, which we assume we don't control, but suppose we can measure that. So let's say this will be the PV generations, for example. And R is a matrix that depends on the resistances on the lines, and then there's some constant. Okay, and therefore, if the network is linear, so this is using linear this flow model, the voltage V depends on Q in this Fi manner. Very simple. Now, of course, more accurate model is that you have this nonlinear dependence on Q, which we don't have, may not have an explicit form. And therefore, we assume V is some function which we don't know what it is, but some nonlinear function of the Q. So that's the model. It's a very general model. The only assumption is that V of Q, this function, is differentiable and is Lipschitz with a constant L, and is Jacobian, is also Lipschitz with the parameter L prime. So that's the assumption of VQ. So VQ can be any nonlinear function as long as they satisfy these two differentiability and Lipschitz conditions. Okay? So that's the model. So how do we? So it generalizes this flow model. Okay. So how do we do this? Let's start with what we know. If the network is linear, how do we do this? And here's a algorithm that Guanan proposed back in 2016 with Lina Li and also Mansa Dalen. So essentially, it's a dual ascent problem for that optimization problem that I showed earlier. Right? So lambda underbar, lambda upper bar are the Lagrange multipliers corresponding to the upper and the lower voltage limits, respectively. And then you can update these Lagrange multipliers based on whether the voltage exceeds the maximum limit or exceeds the minimum limit. Given the update Lagrange multipliers lambda t, then you can choose your QT. So this is your control. You choose your QT in this manner. A is a submatrix that you design. X is the Jacobian. So recall that if it is a linear model, then X is that matrix. XQ is the dependence on Q, and therefore X is the Jacobian V with respect to Q. Okay, so that's the X that appears here. Okay, so this is Jacobian. So you can show that if you do this, and if the network indeed is linear, so we have the right model, then indeed it will converge and satisfy. You will minimize that the software optimization problem, minimize some kind of control effort, where A is measures the control, the effort, the cost of control, basically. That's the matrix A. And satisfy the voltage constraint. So if the network is linear, and if we know the network, then this is a right algorithm that will achieve our goal. What happens if it is nonlinear and unknown? So here's an idea. Let's keep the same structure as before, except that we have to estimate this Jacobian. So we have to compute X hat, right? Instead of knowing what X is. And you can think of X hat as an estimate of the Jacobian. Okay? So let me tell you the result that he got. So he first shows that no matter how you compute the X hat, which is the estimate of the Jacobian, if the error in Jacobian, so X hat is what you compute, and I will tell you an algorithm that he proposed in the next couple slides. This is J is the true Jacobian of that nonlinear VQ function, which we don't know. But if we know the error, satisfy this condition. So you can think of lambda as the cost, right? The Lagrange multiply the cost of violation, right? So lambda k plus 1 minus lambda k is sort of the change in the cost. And this is the weighted sum of the change in cost. And therefore, if the error satisfy this condition, the details of that condition is not that important, then your algorithm here, no matter how you compute X hat, will do the right thing, meaning that it will converge, and you will converge to solve the optimization problem and satisfy the voltage constraint. So that's the first condition. How do we make sure that the way we compute X hat will satisfy this error bound? So here's his proposal. So here's how he will compute the X hat. Right? So there's a bunch of computation you have to do iteratively, but let me just tell you what it tries to do. What it tries to do is the following. So if you look at this, this is a measurement. This is a measure of how accurate your X hat is as an estimate of the Jacobian. So if it is exact Jacobian, X hat is J of t, then to the first order, the voltage and the reactive power delta Q will be related by this. So that's the first order Taylor expansion, essentially, if your X hat is the true Jacobian. Otherwise, the difference is a measure of the error. And mu is some weight, and therefore, the way you compute the estimate at time t is that you look at all the past error weighted exponentially by mu, and you will choose an X that will minimize this exponentially weighted sum of all the past error. That's how you will choose your estimate X hat at time t. Okay, so if you do that, then he shows that indeed your error to the Jacobian will satisfy the conditions that we saw earlier, and therefore it will indeed converge as long as the step size eta is small enough, then it will converge to the right optimal solution where the voltage limits will be satisfied. So this shows a simulation on a SCE distribution circuit. This is the cost remember, that's the optimization in steady state. That's what we want to solve. So if we assume the network is linear and apply the linear control when the network is actually nonlinear, then that's the behavior, that's the cause. Whereas if you use the proposed approach, even though we don't know the network, even though the network is non-linear, we can attain the optimal cause. If you look at the voltages under the proposed control, then they all satisfy the voltage limits. So in conclusion, Guana has proposed a way to do a learning-based feedback voltmeter control that can handle unknown models and also nonlinearity. Okay, so let me tell you the third piece of work, just to make sure the time. Okay, good. So we have time. So this work was mainly done by Zach Lee, who was a former PhD student who is now at PowerFlex. Sunesh Sharma, who was a research staff who graduated from Caltech undergraduate, and then he stayed on at Caltech to do 2 years of research, and then he's now pursuing PhD at Berkeley. And Tongxin Li, who was a PhD student, who is now a faculty at Chinese University of Hong Kong. Okay, so many people contributed towards this effort, and I will mention some of that to building the infrastructure. The people from PowerFlex, the co-founders, George Lee, who was a former student at Caltech, the co-founded PowerFlex, which is a large-scale EV charging company that was acquired by EDF. And then many students over the years and research staff over the years, including visitor students from Cornell, from Lund, Sweden, they have contributed towards this effort, this multi-year effort. I just want to acknowledge them. Okay, so I will tell you the physical infrastructure, which is a adaptive EV charging network, ACN. And just briefly describe what it is. And it is started out as a testbed at Caltech in 2016, and eventually is commercialized by PowerFlex. And then I'll tell you a testbed, open source testbed, we call ACN Research Portal, that's built on top of the physical network, physical EV charging system. Okay, so California has a commitment to have 60%, original 50%, but then become more ambitious. Recently, we changed that to 60% of clean electricity by 2030 and 100% by 2045. And to achieve 5 million zero emission vehicles, which are EVs mostly, by 2030. If you look at the, so this is the duck curve. This is the duck curve in 2021. If you look at the duck curve today or 2021 and say if you want to charge EVs by filling the belly of the duck, then you can charge about 30 million EVs. So there's tremendous potential to charge EVs at workplaces. It can also help mitigate the duck curve problem. EDF Renewable also has a survey that shows that drivers are twice as likely to get EVs when workplace charging is available. So they are probably not going to buy EV because EV charging is available at workplace, but that could be the factor that tip the balance. So the system that we built at Caltech by George Lee, who was a former student, and his brothers and all the other early contributors, is as follows. So this is one of the garages at Caltech. That's the main switch panel in the electric room, which is here, at the entrance of the garage. So George built from the transformer in the main switch panel, he built these 2 transformers and conduits, switchboards, and then he also invented originally a smart EV charger. With the system, then we can, in real time, communicate with the smart charger that he built originally, compute, and also control. So that's what this physical system is. The cyber system is that when driver plugs in their EV, you will use a mobile app to let the system know this is how much energy I need. Say I need 30 miles, and this is the deadline, so I need to leave at 5 p.m., for example. So this information from every driver is sent to the cloud, and the cloud every 2 minutes will solve an optimization problem. So this is model predictive control. It will solve a convex quadratically constrained quadratic program. So you want to minimize a certain cost over the charging rate for every EVI at time t for the next 12 hours. And therefore, you based on your forecast of what's going to happen in the future, you solve this optimal control problem. And then you use the charging rate, the optimal solution for this for the next 2 minutes to charge the car for 2 minutes. And then the next 2 minutes comes around, you update the state, you form the new QCQP, the convex quadratic program, and solve it again. Right? So it's a standard model predictive control. And it is very flexible in that this formulation is highly customizable to suit the needs of different site hosts. If the site hosts want to charge their cars that as fast as possible, for example, you can incorporate that in the cost function C and also in the constraints. If the site hosts want to maximally utilize their on-site PV generation, you can formulate that into this optimization problem. So it is very customizable with objectives that can include cost and PV. You want to charge as soon as possible, and some regularizations to make sure that the charging rates that you compute doesn't jump around unnecessarily. And the constraints can incorporate the energy constraints. So you want to give enough energy for every EV driver before their deadline, for example. You want to make sure that the capacity limits of, say, the transformers, the conduits, the lines, the chargers will be satisfied. So you can incorporate those in the constraint. And every 2 minutes, you solve this convex problem, you figure out the charging rate for the next 2 minutes, and then you repeat. So that's the system. So it was first implemented in 2016. So that's George and his brother debugging late at night, the night before the system was energized. So this was the original prototype that George built. It's a smart charger. He basically used open source chipsets and then built this charger that allow us to in real time communicate with the charger, compute, and then control. So these are the transformers and so on. So initially it was 54 adaptive programmable chargers, and then the 2 transformers and breakers and sensors and all of that. So the system has been operational and expanded, including DC fast chargers now and so on. Since 2016, by July 2020, it has delivered about 1 gigawatt hour of electricity, equivalent to 3 million miles or avoided 1,000 tons of CO2 equivalent. So, and then eventually we started a company to commercialize the technology. The company was acquired by EDF late 2019. So let me just show you some pictures. So this is a picture. So the x-axis is time, the y-axis is the charging rate in amps. There are, let's say, 40 curves, different colors, one for each EV. And therefore, each color curve corresponds to charging rate across time for that EV. So this is January 2018. This is a demo at NREL in November 2018 to use EV charging to mitigate demand charge. So this is the building load at weekends. So there's not a lot of building load, and therefore you can see the duck curve. So this is the net load building minus the PV on weekends. You see the very clear duck curve. This is the weekday, the net curve. You can still see a bit of a duck curve, but you do see a lot more building load and also a lot more fluctuations. The blue curve is the building minus PV, and then the orange curve is building minus PV plus electric vehicles, EV charging. So you can control the EV charging so that the peak doesn't exceed a certain threshold. So that allows you to mitigate the demand charge. This is the effect of COVID. So this is mid-March. You see the drop. So you see this daily pattern and then the weekly pattern. Right? So there's a weekly pattern, quite repetitive. And of course, once the COVID hits, everything shut down. So that was the physical system. Before November 2018 is a test bed. People charge for free, and we can run all kinds of experiments, and sometimes things break and so on. But after November 2018, the operation transitioned to commercial operations. So kind of facilities and the company manages it. So it's no longer, people have to pay to charge. And therefore, it's no longer a test bed that can break. So the idea then is to build a software layer on top of the physical network to provide three things: ACN data, ACN simulator, and also ACN live. So let me tell you each one of them. ACN data takes fine-grained, detailed EV charging data. So these are not only session data of how much energy and the arrival departure time, but also include every 5 to 10 seconds, there's a charging rate from every EV. Right? So it's a fine-grained charging data. You will take the data, so the ACN data component of this research portal will take the data, clean it, anonymize it, and then put it on the web. So everything is open source at this website. So by 2020, there's a lot more now, but 2020 is the 53,000 charging sessions. You can use the data to model user behavior, for example, to evaluate charging algorithms, or you can evaluate the facility or the flexibility of a charging facility, a garage, for example. If it has this many chargers, and it has this kind of arrival patterns and so on. You can also use it to evaluate grid impacts. So there's some examples. So this shows the Caltech weekday, weekend, and also the JPL weekday. This shows flexibility. Is some measure of laxity that the session duration minus the minimum charging time. If you charge at the peak rate as soon as a EV plugs in, which is the industry standard, then that gives you the minimum charging time. And then the difference between how long you took from the real data gives you the laxity at the facility for that user. And this is the flexibility of the facility. It shows that at Caltech, for example, compared with uncontrolled charging versus optimal charging by solving these convex quadratic programs, if you do uncontrolled charging, it takes almost 4 times as much capacity. So you need bigger transformers, conduits, and switchboards, and so on. So that translates to much higher capital cost. Similarly at JPL. So you can use it to use the data to model user behavior. So for example, this is the time when it transitions to commercial operations where drivers have to pay. So the number of charging drops. This is the COVID. If you look at, say, the distributions of the arrival times and the durations, then you can look at the distributions. So one interesting observation is that post-COVID, the arrival times have larger variance. So it's probably because of the flexible hours, and therefore you have more variation. So another interesting learning problem is the following. So you have a lot of charging sessions, but they mostly come from, say, a few tens of cars that belong to a few made by a few manufacturers that use a small number of batteries. And therefore, you would expect the charging behavior would fall into a small number of groups, despite the large number of charging curves. So can we basically, the project is to see whether this conjecture is true, and also if so, can you identify those groups? And the challenge to doing that on the classification side is that we don't know the state of charge of the battery. That information is not available, unfortunately. And therefore, it's very limited information we can glean from the charging curves. Mostly, we have to identify those groups through the classification using the tail behavior of the charging curves. Otherwise, the charging curves, before it gets to the tail phase, they look similar. There's all sorts of issues. And therefore, the issue becomes, given a charging curve, can we extract the tail? Based on the tail, then we do the classification. On the other hand, extracting the tail is not that trivial. It's actually pretty tricky. It depends on how you classify. And that leads to a iterative algorithm, learning algorithm, where you have to extract tails and do the clustering, but then based on the clustering, you have to redo your tail extraction and then do your clusters and so on. So you have to do these iterations a few times before you can classify. It's an interesting learning problem. So that's ACM data and what you might use it for. The second piece is the ACM simulators. So we use the real data to really build a realistic simulation environment that includes the models for the battery, models for EVs, models for the chargers, and the networks and constraints and so on. So these are the physical models of the physical system based on the real data we have. And then we can integrate with ACM data to use ACM data to drive the simulation. We can also use other signals such as tariff, right, such as on-site solar generation. And therefore, you can, if you design a new charging algorithm or even new pricing algorithm, and you want to simulate that, then you don't have to build the basic simulation infrastructure. You can use the ACM sim that provides a pretty realistic simulation environment and run your algorithm, your charging or pricing algorithm interface with ACM sim, and you can just evaluate algorithm. You can also use this to compare across different algorithms. So again, it's open source, extensible. In ACM Live, we use the same interface. So suppose you design a new charging algorithm. You simulate that using ACM sim, and then if everything goes well, if we have ACM Live, unfortunately, it's not completed. I can come back to this point. But the idea is that we can allow you to use your charging algorithm to charge the EVs in the at Caltech Garage. So the interface will capture your command, the charging command, check if it is safe. If it is not safe, then we can just use the default PowerFlex algorithm to charge for the next 2 minutes. Otherwise, we'll use your charging command to charge the real cars, measure the state, send it back to you, and your algorithm will compute the next charging rates for all the EVs in the garage. So that's the idea. So the design is there, some basic information is there, but unfortunately it's not complete before Zach graduated. So anyone interested, please let me know. Everything's open source, you can extend that. Okay, so if you're interested in knowing more about adaptive charging network, the research portal, or use it, here's the website. Zach, he's at PowerFlex now, but I think he's still reachable at this email address. Get in touch with me or with him. Okay, thank you very much.
Thank you, Stephen. Some echo. Okay. Let's thank our speaker, everyone. Thank you so much, Stephen, for amazing presentation. We learned a lot about what are the challenges and how new learning algorithms can help mitigate some of those distribution-related challenges. I'll open it up for question and answer session. Anyone online, any questions, please, you can raise your hand or post it. And the students, you can just raise your hand and I can, you can go ahead with the questions. Okay, go ahead, Ali. I think we are muted out there, so if you can unmute yourself and question.
Okay, so the question is, on one slide you are showing controlled charging versus uncontrolled charging. So the question is, how do you estimate your uncontrolled charging demand? Like, do you have a method of forecasting EV charging demand, or you just turn off the algorithm and let the meter go up?
Right. So this simulation, we use the real charging data, which in this case, for the uncontrolled charging, we assume we use the arrival and also the energy that's actually charged for that EV. And then assume that as soon as they arrive, it charges its peak rate. And typically, the peak rate is limited by the charger. Sometimes it's limited by the car. But we have that information actually because we know information on the car. So I said that when the driver plugs in, they will tell the system 2 pieces of information: how much energy they need and also the expected departure time. They actually tell the system more. For example, what is the car they drive and so on. So they typically will actually register with the system, and those information is already in the profile. So given that, we can figure out what will be the peak charging rate. So the industry standard is as soon as you plug in, you'll be charged at the peak rate. So that's how we can simulate the uncontrolled charging.
And then how about your, like, how do you estimate the departure time? So like, you know, the arrival time as soon as the EV plugs in, and the departure time is also logged in when it goes out.
Right, so this, again, this the graph here, for example, uses, is the offline simulation, meaning that we know the actual charging arrival time, departure time, what the input, but more importantly, what's the actual departure time, what the input of the energy demand they said they need, and the actual energy delivered. Right? So we have all that information offline. So once everything has occurred, then we use that information to do the simulation.
Okay, good.
All right. Yeah, Shruti, go on.
Okay, my question.
Sorry, you got muted. Yeah, sorry.
Okay, so my question is from the model free where you did Newton-Raphson to identify delta V from X, the Jacobian, and delta Q. So my question is actually from that slide, if you go back to that.
Okay, yep. Which slide, say again?
Yeah, I think here, next slide. Yes, here. So actually in this step, you will need to know the starting point, right? When you are doing the least square to fit Jacobian.
Right, so this is just an interpretation of what the X-hat estimate tries to do. The actual computation is this. So there's a bunch of auxiliary variables that you compute. So if your question is what is the starting, so what is the initial state basically of this computation? Yes. Yeah, you can assume anything. Let's say ones and zeros. I think so. If the condition is satisfied, it will converge regardless of your initial state. And
okay, but the system is non-linear, right? You mentioned that the model is non-linear, right? So it will be dependent on the starting point. That's what I was gauging.
Yes, indeed. So the linearity happens here. So this is the V function, which we don't know what that function is. But suppose we can actually measure the value V. So the linearity is embedded in that.
And also you have like meters in all the nodes in this case also?
Yes, this model assumes you measure everything.
Okay, and my another question is from the previous slide. Actually, yeah. Okay, this slide is also fine. How do you this is basically dual ascent approach, right?
That's right.
So dual, how did you penalize when the constraints are violating? Because I don't see any penalty in the objective function.
Right. So this is the.
This is a dual.
Okay. So let me go back to the optimization problem. Yes. Right. So this is the optimization variable, which what we want is that when the control converges, the steady state should be a solution of this problem, right? And therefore, there is a constraint or voltage constraints, and there are Lagrange multipliers associated with the lower and upper bound. The dual ascent method it will update both the primal variable, which will be the Qs, and the dual variable, which will be the lambdas. Now, if things work, then if you do this primal dual update, you will converge to a primal optimal solution and a dual optimal solution. So, and that's what this is. That's what this is. Right. So this is the case if the network is linear and known, then you update the dual. This is just a standard dual ascent algorithm. You update the Lagrange multipliers, and then you just compute the optimal primal given the Lagrange multipliers, and then you just do the iteration. Now, when you don't know the network, and if the network is nonlinear, then you will replace x by some x hat, which you compute through this big set of computations. And therefore, you can think of this case as an approximate dual ascent algorithm.
Okay.
Exact because you don't know the you don't know the Jacobian basically. If you do know the Jacobian, then you'll be exact dual ascent algorithm.
So how did you compute A inverse? What is A inverse?
Oh, A inverse is the cost function. A is in the cost. So we assume we know that. So we assume it's a positive definite invertible matrix.
Okay, and I just have one last question. You have three different lambda in the model. One is lambda upper bar, lower bar, and simple lambda. So here upper bar, lower bar, and I think next slide you have simple just lambda.
Yeah.
Is there any relationship, or they are just like hyperparameters in the model?
No, it is. Right. So basically, the lambda upper bound, lower bound, anytime t, at most one of them can be non-zero. And if we can combine them, you take the difference, lambda under bar minus lambda t, upper bound, right? So that's what combined that's the
Got it. Okay, thanks, Shreyashi. And I think in interest of time, we are going to maybe just one more question, and I'll go ahead and ask. I had a question for you, Stephen. So thank you so much. I think this is very interesting to basically embed the learning systematically in the control problem. I have a question, and it's more of a maybe conceptual understanding. So we do have partial information at least available for these networks, right? Do you see any value of embedding that partial network information in maybe speeding up or in improving these algorithms, or have you done any experiment? Did it help in any particular aspect? Can you maybe talk a little bit about that?
Yeah, so I think it absolutely will be helpful, right? So I think I think black box machine learning based algorithms will be useful when we don't have model. But as you said, for power systems, very often for most applications, we do have some model. We may not know all the parameters in the model, but at least we have the structure, and we may know some partial information. I think all these should be used, and they should be combined with any black box algorithm. Now, how to do that? There's no general theory as far as I can tell. You have to look at each individual applications and also the structure of your networks and problems and so on, and try to figure out a way to do that. But I think that approach, I think, is the right approach. For ourselves, we have done some work along that line, not a lot. I think there's still a lot of potential. So the piece of work also by Guannan in that regard is the following, that suppose we have a model, but the reality is really the model plus an error, which we don't have a model for the error. Then you try to use machine learning techniques to deal with the error term, essentially. But the fact that we have a model, and if the model is roughly correct, then you probably make your overall algorithm more robust.
Yeah, that makes perfect sense. So thank you so much again for spending time with us. And we went a little bit over 12 o'clock, but it was very interesting and very interesting to learn about the EV charging platform. I'll follow up more with you offline on that particular aspect, specifically on the data side of the piece that you are generously making available for research. So again, thank you so much, Professor Lowe, for spending time with us and for speaking to us. And students, if you have any questions, please follow up with you can follow up with Professor Lowe on, over email. You should have the email information available. And we'll thank our speaker again, and we'll call it a day.
Thank you so much. Yeah, thanks for the great questions. A lot of detail. That's excellent. And thank you.
I wish we had more time with you. So I'm sure students definitely have more questions for you. So
sure,
hopefully, yeah. Okay. All right. Thank you, Stephen, again, and have a wonderful day. Bye.
You too. Bye-bye.